Today, we're going on a massive journey, starting from our own familiar solar neighborhood and traveling all the way out to the deep, deep future of the cosmos. You know, space is just so unbelievably vast and complicated, but by breaking it down, we can really start to wrap our heads around just how incredible our universe actually is.
But hey, before we map this all out, do you think you know what the cosmos actually looks like? Because for the longest time, astronomers just assumed that the earliest galaxies in the universe were spiral or spherical, right? Just like the ones we see around us today. Well, the James Webb Space Telescope recently looked at nearly 4,000 newborn galaxies from right after the Big Bang, and get this, they weren't disks, they weren't spheres. They were actually shaped like bananas, or, pickles. It's wild, and it just perfectly proves that space is way, way weirder than we usually give it credit for.
So, to make sense of all these mind-bending realities, we'll be traveling through 4 distinct phases. 1. Secrets of our solar system. 2. Monsters of deep space. 3. Unsolved galactic mysteries. And finally 4. The ultimate cosmic fate. All right, let's kick things off with part 1. Secrets of our solar system. We absolutely love calling Earth the blue planet, don't we? But man, that really just shows our skewed perspective. Earth's water is in reality just this tiny, super thin surface layer coating a giant ball of rock and metal. Now compare that to Jupiter's moon Europa. Europa is roughly the same size as our own moon, yet it packs at least twice the water of every single ocean on Earth combined, all hidden inside this massive subsurface sea. The pressure down there is so incredibly intense that it might actually compress water molecules into this crazy exotic solid state called Ice 7. We're basically talking about hot, pressurized ice just sitting right there on the ocean floor. And honestly, Europa is just the tip of the iceberg here. Our cosmic neighborhood is absolutely packed with bizarre geography. I mean, we've got Saturn's mesmerizing, perfectly hexagonal storm spinning at its north pole. Then there's Mars, with its Valles Marineris Canyon stretching an insane 4,000 kilometers long. But perhaps the most extreme feature of all is Verona Rupes, located on Uranus's moon Miranda. Just to wrap your head around the scale of this 20-kilometer vertical cliff, you would have to stack Earth's tallest vertical cliff, that's Canada's Mount Thor, 17 times. And because the gravity on that moon is so low, if you jumped off that ledge, you'd be falling for 12 terrifying minutes before you finally hit the bottom. No thank you. Now, for a quick human palate cleanser, I want you to consider this number, 96. That is the exact number of bags of human feces that the Apollo astronauts just left sitting on the surface of our moon. Yep. And what is genuinely fascinating about this literal waste is that it's now actually a subject of intense scientific interest. Researchers are desperately wanting to get their hands on those sealed plastic bags to see if any bacteria manage to survive the moon's wild temperature swings and crazy radiation.
So, from leaving human waste behind to ordering deep space delivery, humanity definitely leaves a pretty quirky footprint. Case in point, back in 2001, Pizza Hut paid a cool $1 million to deliver a vacuum-sealed salami pizza to Russian cosmonaut Yuri Uzichov up on the International Space Station. And fun fact, they actually had to use salami because the pepperoni kept growing mold during testing. It's just a hilarious reminder of how much of our goofy, everyday human culture we end up dragging out into the stars with us.
Moving right along, let's get into part 2, Monsters of Deep Space.
716. That right there is the absolutely mind-shredding number of rotations per second of the fastest confirmed neutron star. So when a supermassive star runs out of fuel and collapses down into a tiny, city-sized sphere, the conservation of angular momentum makes it spin insanely fast. It's exactly like when a figure skater pulls their arms in to spin faster on the ice. If you somehow stood on the surface of this star, you would literally be traveling at 24% the speed of light. Just let that sink in for a second. And speaking of collapsing matter, well, that naturally brings us to black holes and something called the Schwarzschild radius. Now, the mechanics of a black hole are obviously super complex, but the basic math of forming one, it's actually surprisingly simple. The really crucial point here is step 2, compressing matter to a critical volume. For example, if you wanted to make a black hole out of Earth, you couldn't just compress it a little bit. You would have to take the entire planet, I'm talking all the oceans, the magma, the metal core, literally everything, and crush it down into a sphere that is less than 1 centimeter wide. That means the entire Earth would be small enough to just pop right into your belly button.
But of course, black holes don't just exist on that tiny theoretical scale, right? They can be unfathomably massive. 100 billion. That is the estimated solar mass of the black hole sitting at the center of the Phoenix A galaxy. This thing is so unimaginably gigantic that astronomers practically had to invent a new class of objects for it, brilliantly called stupendously large black holes. Its event horizon reaches out 3,900 astronomical units. To put that into perspective, that is over 1,000 times farther out than Pluto is from our sun.
Now, what's genuinely fascinating about these luminous extremes is exactly how these giant black holes generate so much energy. See, when a supermassive black hole gets surrounded by a super thick accretion disk of gas, it becomes a quasar. And these accretion disks, they are ruthlessly efficient, converting up to 10% of an object's mass into pure, blinding energy. Take quasar J05294351, for example. It is 500 trillion times brighter than our sun. 500 trillion! Listen, if you were to detonate a hydrogen bomb directly in front of your face, which, don't do that, but if you did, it wouldn't even reach a millionth of that quasar's brightness.
All right, let's shift gears to part 3, Unsolved Galactic Mysteries.
Let's look at the Bootes void. Normally, galaxies are pulled together by gravity into these massive superclusters, right? So an area of space that's 300 million light-years across should easily contain around 2,000 galaxies. But in this one specific spherical region, there's just this eerie, totally unexplained lack of matter. We've only detected about 60 galaxies in there. It's so unbelievably isolated and empty that the astronomer Greg Aldering once pointed out something mind-blowing. If our Milky Way had been stuck right in the dead center of the Bootes void, we literally wouldn't have even known that other galaxies existed until we invented deep space telescopes in the 1960s. We'd have thought we were completely alone.
Which brings us to our final act, Part 4, the ultimate cosmic fate.
Okay, but before we fast forward to the very end of time, we really need to understand how stars, like our sun, even work in the first place. Because here's a crazy secret. According to classical physics, our sun actually lacks the mass to ignite nuclear fusion. It simply doesn't have enough internal pressure to force hydrogen nuclei to overcome their natural electromagnetic repulsion. They just bounce off each other. But there is this quirky little loophole in physics called quantum tunneling that totally saves the day. Because subatomic particles act more like fuzzy probability waves rather than exact little dots, occasionally a wave just randomly pokes through that repulsive barrier. Once that happens, the strong nuclear force takes over and boom, fusion is triggered. Without this one weird quantum loophole, our universe would just be entirely pitch black.
And it's that very fusion that ultimately dictates our cosmic fate. Now, in about 4.5 billion years, we're going to face what's known as the Milkdromeda event, which is when the Andromeda galaxy inevitably collides with our Milky Way. Shortly after that, our sun is going to swell up into a massive red giant. But I want you to consider the sheer, staggering scale of the deep future. Through a painfully slow process of cold fusion, it takes 10 to the power of 1,500 years for atomic remnants to fully convert into solid iron stars. To put that completely absurd number into perspective, you could count every single subatomic particle in the entire universe one by one, taking a full millennium for each one, and you still wouldn't even come close to hitting that number. It's just wild. And then, eventually, after an unimaginable span of time, even the supermassive black holes will just slowly evaporate away via Hawking radiation, leaving, well, essentially nothing at all.
But hey, before we fade away into that deep, dark future, right here, right now, we are facing a truly chilling anomaly. So one of the core philosophies of astronomy is the Copernican principle, right? It's basically the assumption that our place in the universe is in no way special. And yet, recent mapping of the cosmic microwave background radiation perfectly aligns with the Earth's very specific plane of orbit in our solar system, which makes zero sense. There is absolutely no reason for our tiny, seemingly insignificant solar system to align perfectly with the foundational background radiation of the entire universe. As the theoretical physicist Lawrence Krauss points out, this anomaly either means that basically all of science is wrong and we truly are the center of the universe, or something is just fundamentally broken with our larger-scale theories of physics.
So I want to leave you with this one lingering question. If our tiny little rock is inexplicably aligned with the foundational radiation of the entire universe, completely defying everything we thought we knew about our place in the cosmos, what else is hiding out there in the dark, just waiting to be discovered? It is definitely a terrifying, yet totally awe-inspiring thought to chew on. Thank you so much for joining me for this explainer, and hey, keep looking up.